So Makito Oi is going to tell us about symmetry and anti-symmetries in nuclear mean field theory. So very appealing title. So please,
Thank you very much.
Makito, whenever you want.
Okay. I'll talk about symmetries and anti-symmetries in nuclear mean field theory, but basically this is closely related to the calculation of generator coordinate method. Okay, the pairing correlations which are responsible for the superconductivity and superfluidity stimulate the many-body physics for a long time. And the nuclear physics also employ this concept of the pairing. And with the pairing, we can explain, for example, deviation of the moment of inertia from the rigid body value, as demonstrated by Pius and Yakots and the Motors and Valentin. Bogolubov also made an important contribution to this study. The pairing correlations are taken into account as a superposition of many Cooper pair states, and they can be expressed in the so-called Thales ansatz. This one, where Z here is a skew symmetric matrix. This many-body state is also known as Hartree-Fock-Bogolubov or HFP states in nuclear structure physics. It breaks the number conservation, although the average is constrained, like here. And of course, this is a mean field approximation, so the energy, the average energy is constrained. Wheeler et al. Proposed a theory going beyond the mean field theory called the generator coordinate method, or GCM. In GCM, the more complex many-body correlations are taken into account by superposing many HFP states, which are, for example, parameterized by the deformation parameters. In this case, the superposed state can be regarded as a collective oscillation of nuclear surface, if this Z is considered as a deformation parameter. But of course, you can choose as many different kinds of parameters as possible, like other dynamical variables. In solving the GCM equation, or Hill-Wheeler equation written about here, one needs to calculate the overlap functions between different HFP states, because the HFP states are taken as non-orthogonal basis to expound the nuclear many-body states. And this part is called energy overlap function, and this part is called norm overlap function. This equation looks like the energy eigenvalue equations, but because of the non-orthogonal basis nature of the Hartree-Fock-Bogolubov states, this n remains inside the equation. At first glance, the norm overlap function looks like a transcendental function coming from the exponential operator here. An expansion of the exponential operator up to the infinite order sounds quite a painstaking jobs to do. Look at here. When you calculate the norm overlap kernels, norm overlap functions, you must calculate this quantum quantity, and the wave function contains exponential operator. We need to sandwich the two exponentials between these two vacuum state. And in principle, if you expand this exponential operator, we have to carry out many creation annihilation operator expectation value. Therefore, in the beginning of the early stage of the study, many people satisfy themselves only with an approximation of truncated Taylor expansion in the exponential part to have approximation for this quantity. In 1960s, using the linked cluster expansion approach, Onishi and Yoshida were successful in obtaining the exact and compact formula for the HFB normal overlap function, which has a form of the square root of determinant of this matrix. And this Z comes from the HFB and Z, which is skew symmetric. And the I represents the identity matrix. In the original linked cluster expansion, the partition function applied to the quantum statistical mechanics is considered, and the theorem says that its logarithm is equal to the sum of the connected diagrams, all the connected diagrams. From the similarity in the mathematical structure, one can apply this theorem to the HFB norm overlap functions. In the case of the partition function, the exponential structure comes from the Maxwell-Boltzmann distribution. But in the case of HFB theory, it comes from the superposition of many particle states. So in the case of HFB normal overlap function, the logarithm of this quantity can be written in terms of the connected diagrams, the sum of all the connected diagrams, where this A operator is the Cooper pair annihilation operator. And carrying out the detailed calculations, you can have connected diagrams can be expressed as this kind of quantity, which is the power of this matrix, which comes from Thaler standards. This is a product of the two skew symmetric matrices. And this matrix has no particular symmetry or property like Hermitian or unitarity and so on. Although the Onishi formula was successfully applied to numerical calculations in 1980s by Hara, Hayashi, and Ring for the ground and the low spin states, I found a serious problem in 2005 in this and published in this paper, applying the Onishi formula to cranked HFB states at the high spin. The problem is referred to as the sign problem in many cases, which I call the nodal line problems, which is the zero of the norm overlap functions in the Euler space. So this is in the framework of the angular momentum projection. So you have to rotate the HFB states by applying the Euler angles. And in this Euler angle space, you find systematic geometric structure of zeros of the normal overlap functions, which forms like a ring. In general, the skew symmetric matrix Z is a complex matrix, this one. So that Onishi formula provides complex function with a square root, which is a two-valued function unless Riemann surface is properly set. This mathematical nature in the Onishi formula is a source of the sign problem. This determinant of this matrix element, this matrix is a complex function of Z or Z prime. Therefore, taking a square root of this complex function gives rise to the two-valuedness. And that is, in the case of the square root, the two-valuedness can be represented as the plus or minus ambiguity. Usually, physical quantities, all the physical quantities are expected to be single-valued. And there is no reason why we have to doubt this property to be violated in nuclear structure physics. In the linked cluster expansion, we made use of the transcendental properties of the exponential That is, we consider the sum over all connected diagrams up to the infinite order. However, we should remember that the nuclear structure physics belongs to the many-body quantum physics with a finite degrees of freedom, as Professor Lobachevsky pointed out. In the calculation of the many-body states in nuclear structure theory, the Hilbert space is spanned by the single particle state with a finite model space, dimension m, which is represented here, m. So any single particle states, in this case, this is a pairing creation operator, but this index is expanded up to the model space dimension, which ends at m, because we are dealing with the finite systems. Based on this nature, one can demonstrate that the norm overlap function is a finite series. So the exponential, if we expand in terms of the Taylor series expansion, we expect that the series continues up to the infinity, but actually it ends at the finite term. Why that happens? It is because the Fermi statistics, because the nuclear systems, nuclear many-body systems, is many fermion systems. So we have to put the same identical particles in the same states. So as we expand the exponential to the higher order, there are certain terms which contains more than particles which are given to constitute the nuclear systems. For example, if we have m particle systems and we go to the higher terms beyond the mth term, we have to put more the more particles and the multiple particles into the same states, which gives rise to zero metrics, zero coefficients for the expansion of the exponential. From this consideration, one can say that operator of exponential z looks like a transcendental operator, but it is a polynomial in the framework of the finite many-body theory. Following this consideration, one may expect that the HFV normal overlap function can be expressed in terms of polynomials rather than infinite series seen in the linked cluster expansion. In the HFV normal overlap function, if the HFV normal overlap function is expressed in terms of the polynomial, then the sign problem or multivaluedness of the function is no longer a problem, because polynomials do not have any problems coming from the branch count in the Gauss plane. This alternative approach is attempted by Professor Robledo, and his work led to propose a new formula expressed by the Faffian, a kind of polynomial similar to the determinant. And his work was published in 2009 in Physical Rapid Communication. Interestingly to me, Professor Robledo used the fermion coherent state, which is expressed in this way, to achieve, to bring the polynomials called Faffian into the nuclear structure physics. Inevitably means that this fermion coherent state contains a number called Grassmann numbers. This Grassmann number has very strange, special properties in algebra and calculus, way to calculate this number, which is called the Grassmann algebra, which follows the anti-commutation. And how to say, this is a number, ordinary number, but follows the anti-commutation. And the Grassmann numbers are usually employed in the functional approach to quantize the fermionic or Dirac fields in quantum field theory. The original motivation to introduce the fermion coherent state was to replace all the creation and annihilation operators into Grassmann numbers like this. We are interested in the expectation value of products of creation and annihilation operators. By using this identity operator based on the Grassmann algebra, we can replace the annihilation operator and the creation operator into a Grassmann numbers because fermion coherent state is designed to have the eigenstate of annihilation operator and creation operator in a dual space. And the essential part in the evaluation of the overall function is the vacuum expectation, this one, of the product of the creation and annihilation operators for fermions. In the HFB case, the product follows a special ordering. In the HFB case, this ordering naturally comes to appear because it's a pairing state. So the C dagger, C dagger, C dagger, these pair states is placed in the right hand side of the expectation value. And we take the complex conjugate of the wave function. Therefore, the pair annihilation state sits in the left-hand side of the expectation value. Therefore, this ordering is naturally realized in the norm over the function for the HFB states, and which is quite useful to apply the, this Grassmann fermion coherent states, because the ordering of the Grassmann numbers follows in this way. So Guzai, 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 and the Guzai star, Guzai star, Guzai star, and so on. And this arrangement can be restated in this way. And this is first discovered by the professor of Ledo. And before Robledo's work, this Gaussian type integral using the Grassmann numbers are known already. For example, if you look at the Negele-Oland textbook, this formula is explained in the quantum field theory part, and which gives the determinant of this matrix. But what Professor Robledo found is that arranging the Grassmann numbers in this way, he found the different types of Gauss integrals with respect to the Grassmann numbers. This Guzai, this arrangement of the Grassmann numbers from Guzai 1 to Guzai m forms a vector of Grassmann numbers. But in this expression, the Grassmann number vectors are extended from Guzai to Guzai star in this way. So the dimension doubling was employed to have this expression of the Gauss integral. And in Robledo's paper, it is called the bipartite expression. But this bipartite expression is often employed in the superconductivity theory, like BCS. Creation and annihilation operators are treated at the same time to form quasi-particle creation annihilation operators through Bogoliubov transformation. Yes, and what is truly amazing is that this new type of Gauss integral gives rise to Faffian, which is similar to ordinary type of the Gauss integral with respect to Grassmann numbers, gives rise to determinant. And if you this identity is not known for nuclear physicists until Professor Robledo found, but if you look at the mathematical textbooks, this formula is known for long. And it should be noted that the Faffian, is defined exclusively for skew-symmetric matrix, unlike the determinant. This A matrix can be any matrix, Hermitian or non-Hermitian, symmetric, anti-symmetric. For any matrices, you can calculate determinant. But to calculate the Faffian, this M must be skew-symmetric. So it is very important to find the, proper matrix here to form a new type of Gauss integral, because M must be skew-symmetric. So if we start from this skew-symmetric matrix set, and cluster expansion, the connected cluster expansion is some of the powers of this Z star Z prime matrix, which is nothing. I mean, which is quite general, does not have any particular symmetries or properties. Therefore, it is very important to connect this general matrix to skew-symmetric matrix, which should be placed in this part of the Gauss integral, which will be displayed later. Sorry. Now we have two formulae for the HFP normal function, but their analytic behaviors are very, very different. The Onishi formula has algebraic expression, and it suffers from the multi-valuedness due to the square root of a complex function, whereas the Faffian formula is expressed in terms of polynomial and has no singular problems. One may wonder why such a difference emerges from the common starting point. The answer to this question is a way to handle the infinity and the finiteness. Basically, the HFP normal function is a polynomial that is finite trace due to the Fermi statistics, even though the theory standard has an exponential operator which comes from the Lie group operator. This property is realized thanks to the, from this point of view, the Faffian formula is a rather natural way to describe the nuclear many-body states rather than linked cluster expansion theory. However, there are many theoreticians, many nuclear physicists, theoreticians, who are familiar with the quantum field theory and Green's function approach and tempted to use the linked cluster expansion because of the similarity. By regrouping the diagrams into the connected and disconnected diagrams, the higher order terms, which are vanishing due to the Fermi statistics, are forced to gain certain values and they contributed to construct an artificial infinite series by force in the name of the connected diagrams, which means that if we employ, this is the each term of the result of the expansion of the exponential operator, and you have connected diagrams and disconnected diagrams. But when you apply the linked cluster expansion, only the connected diagram survives. But in principle, the norm overlap function of the HFE states are polynomial. That means contains the finite terms. So it ends some term here, which corresponds to the model space dimension. So the higher terms must be 0. So summation between the connected diagrams and disconnected diagrams at the higher terms needs to be 0, 0, 0, 0, 0. But if you apply the linked cluster expansion, you have to have an infinite series only in the connected diagrams. So the cancellation between the connected and disconnected parts at the higher terms needs to be disentangled, and you have to give some values to these higher order terms in the connected diagrams. So this is, in a sense, unnatural, but the similarity between the quantum field theory and nuclear many-body physics must be, how to say, attracting theoreticians to employ this kind of approaches. That's why, that's why Professor Onishi probably employed the linked cluster expansion. But as a result, the determinant and the square root comes to play, and it gives us sign problems. There are two approaches presented so far, which is the Onishi formula, and numerical implementation was done by Hara-Hirschwing, which were partly successful, and Robledo's Faffian formula, which is perfectly successful in a sense. But we have some questions about relation between infinity and finiteness. And I believe that these two approaches are connected through the Neugard-Wist method, which were proposed in 1983 between Fafian formula and Onishi formula. However, the Neugard-Wist formula received rather negative reputation so far, except a few practical applications. For example, Avets and Bender wrote in their paper that the practical application of the NW technique becomes cumbersome in realistic cases and has been rarely used in practice. These comments I received many times from many people. Dr. Schmidt employed Neugard-Wist method to his vampire approaches, and this is known to be successful. And Professor Robledo wrote once in his paper that handling the eigenvalues of non-Hermitian matrices is a difficult task that increases its complexity if the pairwise degenerate eigenvalues have to be obtained numerically without any symmetry enforcing degeneracy. I strongly agree with these comments because when you look at very general metrics, you may wonder whether this general matrix gives rise to perfectly degenerate eigenvalues in the end of the calculation. And slight contamination coming from the numerical errors may disturb the calculation. So this is what Professor Robledo commented in this paper in 2009. And I started with this impression and started to do the numerical calculations based on the algorithm of the Neugard-Wist formula.
Makito, sorry,
Yep.
You have 5 minutes left.
Sure. The principle of the Neugard-Wist method is that the eigenvalue of z star z prime, which comes from the Hartree-Fock probability of states, needs to be perfectly doubly degenerate. Because of that, the square root disappears. So when you calculate the norm over kernel, you choose one of the degenerate eigenvalues to form a product in this way. So you need to choose half of the dimensions of the matrix, because the other counterpart is degenerate eigenvalues. And for example, if you have two different skew symmetric matrices and has this kind of matrix I plus AB, and you are required to calculate the determinant of this very general matrix, you might not expect that the eigenvalue of this matrix is perfectly doubly degenerate. But according to the Schur's complement, this mathematical structure can be rewritten in this way. And if you look at this part of the matrix, this is skew symmetric, B minus A. This is the skew symmetric matrices. And I minus I, this forms the skew symmetric structure. And this quantity is exactly the matrix that Professor Ledo found in completing the new type of Gauss integral. And of course, with a well-known formula for the Faffian and the determinant, you can write this formula in this way. So the worry of the eigenvalue problems for the no symmetry is actually turns out to be related to calculation of Faffian or determinant of the skew symmetric matrix. Therefore, in the beginning, people may wonder whether we can perfectly calculate the doubly degenerate eigenvalues from the very general matrix, but because of this hidden symmetry and the hidden relations, it seems that there is a guarantee that we can perfectly calculate the doubly degenerate eigenvalue spectrum for this general matrix at a glance. Based on this consideration, we have new norm overlap formula, which were published in 2018, and we extend this line of investigation to further to calculate general matrix elements of general operators. Okay, let me summarize. The Schur's complement gives rise to the connection between general matrix, determinant of general matrix to Faffian or determinant of the skew symmetric matrix in a bipartite expression. The origin of the sign problem in this formula is the infinite series coming from the application of the linked cluster expansion. The reason why the sign problem does not exist in the Faffian formula is that it is a very natural expression of the finite many-body nuclear system. And the Newgard-Wist method can be regarded as a bridge between infinite and finite. Thank you very much.
Thank you very much, Makito.
Thank you.
We have now time for questions or comments.
Yeah, so I have a comment. Pairs of eigenvector matrices are simply related to one another. It is easy to find degenerate eigenvalues. Okay, thank you, Jacek. I will take a look at this. Let's go review. C62 2000. So 17301. Is this a paper written by Jacek? You?
So maybe
yes, it is.
Okay. Okay. The questions.
Are there other questions or comments? Okay, I have one question. have you compared the results of the different overlap formulas for example, whenever you have or you haven't some intrinsic symmetries? For example, if you have symmetry conserving wave functions, and then you apply all these formulas, or if you have, for example, cranking, then what is the difference between the different formulas?
Applying a cranking calculation doesn't change any mathematical structure, so the same conclusion can be drawn for cranking calculation.
Mm-hmm. Okay, Luis Robledo wants to say something. Please, Luis.
Yes. Thank you, Thomas. Very nice talk, Makito.
Thank you very much.
I just wanted to point out something that probably has been lost in your talking, is the fact that obviously the Nedgar and Boost method is correct. I mean, and it's obvious that you can guarantee that the eigenvalues of this matrix C prime that appears in Nedgar and Boost method has doubly degenerate eigenvalues. This is true. I mean, and it can be proven mathematically. But the problem with this method is that you have to find those eigenvalues numerically. And you have to modify the methods used usually to determine those eigenvalues numerically. Otherwise, you are going to find eigenvalues which are not exactly the same, and it's difficult to really tell which are the pairs, eigenvalue pairs, right? Whereas on the other hand, by using the Faffian method, you have a method that has this symmetry built in, so you don't have to worry about any numerics.
Exactly.
And the second thing is that the numerical cost of the Faffian is equivalent to the numerical cost of the determinant, which is much less than the evaluation of eigenvalues. I mean, I find an advantage to have the Faffian formula mostly because of that. I mean, you don't have to worry about the numerical problems, first thing, and second thing is much faster than evaluated eigenvalues.
Exactly. Thank you very much. Yes, yeah. I agree with you that because of the Faffian new formula invented by you, we don't need to worry about any mathematical and numerical problems. So we are very relieved to have the correct final absolute correct solutions for the many-body states. But some people are not familiar still with the Faffian itself, and many of them are familiar with the determinant. So some of them wants to carry on the determinant calculation rather than Faffian. So for these people, telling them that there is a method called the Newgard-Wist method, which is based on the determinant calculation, and you don't need to worry because of the mathematical nature. There's I don't know perfect guarantee, but some guarantee that you may find a good degenerate eigenvalues in your calculation. So just go on. So if there is a difference between the Faffian formula and the Newgard-Wist formula, then there is a serious problem in numerical calculations. But if you confirm at least one case that there is a consistency between these two formula, then you don't need to worry about the numerical errors in determinant calculation based on the Newgard-Wist method. So for the continuing calculations, you can go for the determinant calculation of the Newgard method. What about this? This is the basic ideas about why I'm interested in Newgard-Wist method. Guaranteed, like a Faffian method is like a life insurance that you don't need to worry about it, because in the end, the Faffian can protect you from the numerical errors.
Mm-hmm. Okay, thank you very much. I'm afraid that we are really behind the schedule. So let's thanks again Makito Oi, and I'm going to thank him on your behalf.
Thank you very much.
And now we have a coffee break, and I suggest